And the good news is that I think I'm beginning to have confidence in this class. Yeah. So I begin to have confidence in this class. If you notice, I've started recording. I've put in your grade for question 1. So, of course, today you're going to see all the grade you're going to be in. So, with what I've seen so far, I believe that I've been a kind of tremendous improvement in grade. But if there's anyone who is still struggling with the class, please make sure you let me know. Today, we actually going to walk you through another exciting topic in statistics. Of course, like I said, statistics is like a story, right? A story that goes on and on and on. Now, in today's topic, we basically going to focus on, Van Bertalanffy growth models. But let me just tell you this, how do we find ourselves in a situation where we basically want to focus on this kind of models? We find ourselves in a world where we are trying to study and understand the kind of relationship between variables. And if we want to seek redress from statistical point of view, what we are normally want to do is basically to figure out what the model is going to be that will adequately represent the relationship between the variables. And let me tell you, there's no much difference between what we do in statistics and what they do in machine learning. The difference is just like in statistics, we basically begin by specifying the model, by specifying a particular model using what I call the principle of subjectivism or based on experience. And of course, we have a way to validate whether the model is adequate or not. But unlike, in machine learning, it's more or less like, we have results already, and we basically, okay, if I have X, X gives me Y. I have inputs and input give output. Now the question can I figure out a function that an algorithm, that will help us to figure out the function that actually relates the input to output. So they believe that the algorithm is basically going to figure out that, but the bottom line is just like the two of us were looking for a particular model that will adequately capture the data. Now, take a look at this. In this course, we started by fitting a linear regression model. And of course, we stated assumptions under which the linear regression actually hold. And of course, I remember I walk you through when you have combination of predictors in a model. Of course, we also have situation whereby the relationship may not be linear in parameters. Okay, when the relationship is not linear in parameters, of course, we have what we call a non-linear models, but there are several forms of non-linear models. But broadly speaking, we can classify non-linear models into two. We have the intrinsically linear and the intrinsically non-linear. And what we mean by the intrinsically linear is more or less like, okay, I have a non-linear relationship and I try to apply a mathematical technique of transformation, and at the end of the day, I was able to linearize. Now, I wanted to take a look at this. We're not talking about solving the problem of normality or no. What we're talking about is able to linearize a function using mathematical technique. And what is the idea behind linearize? By able to linearize the function, then we can apply the conventional method of estimating parameters in linear model. But in a situation where we try to linearize that's a nonlinear function, and it doesn't really work, then we have an intrinsically nonlinear model. And the way how to estimate parameters for intrinsically nonlinear model is to go by way of Taylor series, where we're basically going to approximate the function. Approximate the function means we're actually going to use what I call an iterative procedure. Now, on Monday, I walk you through some growth models, under nonlinear models. An example, logistic growth model. I remember we used that to model to project U.S. population, but today we're actually going to go visit another important growth model that we call, Van Bertalanffy growth models. Okay, the outline, of course, I've already revealed the linear and the nonlinear models now, and I'm basically going to go, straight to business with the Van Bertalanffy growth model. Now, I need you to pay attention. This particular model is very, very important. Now, this is the specification. Of course, why am I specifying this? We are thinking statistically. In statistical analysis, of course, we're basically going to start by specifying our model. Okay, now when you take a look at this model, of course, the response variable here is the length at the time. Of course, when you see an expected value of length at the time equal to that, that's a mean function. Okay, this is an example of a non-linear mean function. Okay, a non-linear mean function. Okay, now when you see the expected value of at is just the expected, or the average length at time t, which is the response. And the L infinity is talking about the asymptotic average length. Now, let me tell you this. This is not maximum length, okay, because this is just an average. Of course, maximum, some animal or let me say any living, whatever, could have a length that is bigger than that. Okay, that's why we call that an asymptotic average length. Then we have a K that we call the Brody growth rate, and we have a T0, which is a modeling artifact, which is set to represent the time or age when the average length is 0. This reminds me of y-intercept. You remember the y-intercept. Okay, so the T0 here is synonymous with that. So that represents the time or age when the average length, when the average length, sorry, not y-intercept, that should be x-intercept. In mathematics, we have y-intercept, we have x-intercept, y. The y-intercept is the value of y when x equal to 0. And the x-intercept is the value of x when y equal to 0. So here we're talking about, time or age when the average length is 0. So we're talking about when the response is 0, what was the, x. Okay, so take note of that. Okay, so this is the specification of the growth model. Okay, this is Van Bertalanffy growth model. But let me tell you this. Looking at this growth model, the statistician did not arrive at this model by accident. The statistician actually go mathematical. The origin of this model is this. Because the rate of change of length, okay, is directly proportional to the change in the L, that L infinity and then L of t. That's what you say. So this is the origin. It's a differential equation. Has any one of you heard about differential equation? Like that's a first order differential equation. Okay, now if I actually seeking to get the L of t, the length at a particular point in time, then it means I'm actually need to solve the ordinary differential equation. Of course, I can use the method of separating variable here and integrating both sides. That we actually arrive at what I have here. Okay, I'm actually going to arrive at this if you follow what we're trying to do using the method of separating variable in ordinary differential equation. So where I'm going to integrate this side now, I also want to integrate this side. Of course, I'm going to have this equal to that. And the log here is going to go to the other side and become exponential. Now I have this. Then I need to impose an initial condition, okay, that I said the other time, okay. I need to impose an initial condition, you know, where the length equal to 0 that I just talked about, okay, the XL intercept. Okay, at the end of the day, I will be able to get my D. Then I'm going to plug in that values of D into the expression. Then I'm basically going to have, finally, I have the model, the Bertalanffy model that I talk about. Let me tell you this. Every statistician is also a mathematician. Okay? Every statistician is also a mathematician. I remember when I was doing my PhD in statistics, and some of my friends that have problem with statistics, I said, you don't have a statistical problem. The problem you have is mathematical problem, because you know, PhD in statistics requires that you should have very solid foundation of mathematics. Okay, so this is a von Bertalanffy growth model, okay, where we're actually relating the lengths, okay, at the time t, okay, with the average asymptotic length and some other factors like that. But you know what? When we're talking about growth, it is not always about length. What about weight? Okay, so when you want to notice, the only way you can notice a growth is through certain expression when you observe an increase in length, or you express an increase in weight, okay, at, you know, when age increases. Now take a look at what I have now. In the specification of the weight, okay, in the specification of the weight, we're actually going to exponentiate the length, L of t, that we got the other time. You know, the L of t, okay? When I put it in here, L of t, so you know, there are two parameters, A and B. When I put the L of t, so the whole of this is the Bertalanffy for length. So, of course, there's a relationship between the weight and the length. Okay, now this is the weight now. The Bertalanffy version of a weight. If I want to determine weight at any particular point in time. Okay, do you understand that? Okay, so I just gave you an expression for the length and for the weight. But you know what? There's one particular animal that we're going to focus on today, and of course the Van Bertalanffy, Francis, the like, the focus on that animal, which is this particular animal. Has anybody seen this animal before? Okay, you seen that, right? Okay. Now we want to focus on this. In fact, there was a research I think conducted by Old Dominion University. The research was conducted by Old Dominion University. Okay, in conjunction with Virginia, Virginia Marine Resources Commission. Marine Resources Commission. I think we call them UMRC. Okay, now they make use of, they basically focus on predicting the growth, in fish. Okay, the growth, of course, if you want to do that, we talk about, predicting, study the length and study the weight, okay, when you put into consideration the age of fish. Okay, so now we have data. The data we're going to be using here, if you load those packages, FSA, the FSA data, the library NLS. The library NLS too, because the model we're basically going to be using is a nonlinear model. And of course, we're going to be using a nonlinear least square. And don't forget, the nonlinear least square, we actually need to figure out what we call the initial starting point. Oh, can you hear me? You can hear me, right? Okay, so initial starting point, and from there, we'll be able to optimally obtain the parameter, the estimate of the parameters of the model. Now, the name of that data set is called croaker 2. In fact, they call it Atlantic croaker. I'm actually going to give you a zoological name for that. Atlantic croaker. The zoology name for that is Micropognias udilatus. Okay, that's a like zoological name for that particular, the animal that we actually want to talk about. So now we want to focus on in this we have males, we have females. Okay, male fish and female fish. But when you take a look at the first, we basically want to focus on males. Okay, when you take a look at this particular, the data set, it's like a subset of the whole data, right? We want to focus on male, okay, male fish. Okay, and focusing on male fish, what we actually want to talk about, we want to have an estimated mean function. This is what we actually take a look at this. This is the mean function that we actually want to derive because looking at the data that we have age of the fish is recorded, and not only that, the length and the time as well. Okay, we have information. I can even show you. Give me 1 second. Let me see if I have. Yeah, here. Okay, so you have the age, the length, and the sex. Okay, like I said, we're only focusing on male. Okay, so take a look at that. So, and then of course, the model we are seeking. The model we are actually seeking is, that guy. Okay, that's what we want to find, right? Okay, so and there are two parameters in this model. Okay, there are two parameters in this model. This is a parameter. This is a parameter. Okay, this guy and that guy. Sorry, three parameters. This. We got three parameters. This guy, this guy, this guy. Okay, this guy, this guy. Sorry, this guy, this guy. So the L of infinity is the one I call the asymptotic average length. Asymptotic average length. This is the one I call the Brody rates of growth. And this guy is probably the S-intercept that I talked about the other time. I talk about S-intercept, okay, the average maybe year or time when the average numbers of length equal to 0. Okay, now if you want to actually run this now, four of us need to get our initial values. Don't forget, the model we are seeking is basically, a nonlinear model. You get what I mean? So we need to get, our initial values. Of course, this will give you, these are the initial values now that we have obtained. You can see the code, okay? And after that, then you run the model, okay? Putting into consideration, okay, the initial value, okay, the S typical is actually all this, okay? So then when you write the overview is more or less like the same way you do summary in linear regression, okay? Now, when you do that, you're basically going to have this. Take a look at this. This is what you're going to have. This is the result. This is looking like output in linear regression, right? You got three estimate, right? Take a look at that. The L infinity, when you see INF, that is the same thing as L infinity, okay? The same thing as L infinity. So this is this guy here, okay? So take note of that. Okay, so this is the K, this is the T0. So take a look at that. Okay, so this is a result, okay, that we have. Based on this now, you can write the non-linear, the estimated mean function, right? Okay, just like the similar way. Now, this is a confidence interval. We also want to get, when you take a look at what you have under the estimate here, these are point estimates, a point estimate is when you have a single value, right? Okay, so then we also need to get the interval estimate. The interval estimate is what we have here. Okay, then we can get a correlation. But let me tell you this. before going into this, because this is something that has to do with time, right? We expect the variables to be correlated. There's no problem about that. That's what you can see, high correlation. You see that? They are highly correlated. The parameters should be correlated, okay? That's expected. That's no big deal, okay? But what is a big deal here is it is mathematically proved and statistically observed that when you are working with a non-linear model, I'm going to say that again, when you are working with a non-linear model, we may not be able to toss the confidence interval because we are assuming, last asymptotic last sample theory, which may not be true. Okay, because of that, we go for bootstrap. Okay, we go for bootstrap confidence interval instead of relying on the other one. So this is the bootstrap now. Okay, this is a bootstrap confidence. But what am I bootstrapping? I'm bootstrapping the fit typical. I'm going to show you, I'm going to walk you back to the fit typical, which is this guy here, the model that we have. You see that? That's what we are bootstrapping on, okay? Now, when you do the bootstrap, you can have opportunity to look at the histogram. This is going to come out from the bootstrap, okay? That will enable you to see clearly yourself the distribution of each of the parameter. For the head infinity, you'll be able to see that for K and for T0. And what you can see here, you're basically going to see that this is the one that is approximately normally distributed. So this guy and this guy, they are skewed. So, and that is the reason when you compare the confidence interval, the bootstrap confidence interval, with that of the the normal theory confidence interval, you're basically going to see there's going to be a huge difference in what you for the L infinity and T0. What happened is because of the fact that they may not be normally distributed, and you can see the reason why you cannot trust the other one. You cannot trust because the other one, don't forget, the other one actually rely on the fact that the beta, the parameter follow normal distribution. And as you can see in the bootstrap now, it's trying to tell you it's only one. Okay? It's trying to tell you it's only one that follow normal distribution. Okay, so the next thing we can do, we can conduct hypothesis about K. Okay? That very K. You can test K is K equal to 0.5 or less than 0.5. Okay, so if you want to do that, you're actually going to conduct the H test, on the both typical. Okay, your hypothesis should not be on the conventional one. You can see violations, right? That I show you when I was showing you the histogram, right? And that's why you're basically going to focus on the bootstrap. Okay, so. And of course, you look at the p-value here, and which means there's no enough evidence to conclude that K is less than 0.5. The K is basically the Brody, rate of growth. Okay, the Brody rate of growth. So to see whether it is less than that or it is equal to that, then we can make a prediction with our model. Okay, now we can make a prediction with our model when we plug in the values of H. Of course, when you take a look at the model, or we go back to the main function, the moment I know L infinity, I know K, I know T0, then any values of T, I can plug that in and determine the L of T. You understand? But it depends on whether absorption holds. Because let me tell you this, as we have the absorption that we have in linear regression, we also have that in non-linear, which I'm going to discuss with you. But let's first pretend like, let's see, let's plug in, for instance, maybe a fish. It's actually the age of a fish. If it is 8, when I plug that in, then this is giving me the length of that. Can you see that now? Okay, and I can also obtain what I call the confidence interval associated with my prediction. We also do that. We did that. you know, in when we're dealing with the linear regression. So as you can see, this is a point estimate for the length when the age of that fish, we're talking about male fish here, is age. This is the point estimate of the length, and this is the confidence, you know, interval, you know, trying to say that the mean length of all, you know, age 8 male Atlantic coca is between 341 and 358. Any question? Okay, so far so good, right? Now, let me tell you this. The prediction we are making here is only valid provided assumption hold. You know, let me tell you this. Statistics is so beautiful because of the fact that we acknowledge the fact that error exists. The existence of error enables us to know how valid is our model. Okay, now, you know, when you're working with a nonlinear regression model, of course, we require that, you know, normality assumption hold. We also require the assumptions of constant variance to hold. We also, even though assumptions of independence may not hold, because we're talking about time. These are time, you know, like a time series data, but there's no problem at all. You get what I mean? Now, of course, if I want to check, you know, whether the, you know, the normality or whatever, or homoscedasticity assumption hold, I can go by the way of getting the residual plot. Now, residual plot is not used to test for linearity. Don't forget, in linear regression, we use residual plot to investigate linearity and constant variance. But the residual plot here, we're only talking about investigating constant variance, because we know we're using nonlinear, right? Okay, the histogram that you see is the histogram of residual. You know, in linear regression, we're using a QQ plot, right? We have other graphical ways to investigate whether normality assumption hold. Okay, now, as you can see now, so you know, there's a slight variability with increase, you know, with increase the fitted values, and of course, as you can see here, the histogram suggests a slight skewed. You know, when you take a look at this, slight skewed, okay? And if you take a look at this, so, you know, which is trying to tell us, okay, we have some form of violations. You get what I mean? But let me tell you this. The model that we use, that we call L of t equal L infinity, you know, 1 minus exponential raised to power k, or t minus t0. This particular model that we use, the error actually comes, you know, the error comes in additively. I'm going to say that again. What we have fitted to get all the way today, we assume error actually comes in additively. Okay? Now, we can also have another situation where error does not come in additively, but error is going to come in multiplicatively. Take a look at that. I'm actually going to have this guy, 1 minus this guy, t minus t0, then ui. You know, when it comes in multiplicatively, okay, taking a log, okay, it could be linearized. You get what I mean, right? Okay. You know, we may want to consider two different kinds of error structure: additive error structure and multiplicative error structure. Okay, that's what I want to talk about here now. Multiplicative or log normal error structure. And I'm going to tell you this. You know, I want us to reason together. The idea of a constant variance. What it's trying to tell me now, the variability in the response should be the same even when S changes. Now it's trying to say the variability in the length of fish should be the same for fish, for age 1 fish, and even for age 10. That's what it's telling me. That may not be possible. Okay? Because smaller fish, it will look alike in terms of length. That's all, you get what I mean? So the variation may not be the same. Okay? which means we could be expecting a constant, violation of that constant variance assumption. But the way out, of course, the way out is when the error comes into the model multiplicatively. That will enable us to take the log. Don't forget in the exam, midterm too, when you experience the problem of heteroscedasticity, you take the log, right? What happened at the end of the day? You conducted a Bridge-Pagan test and we were able to fix the problem. Because error comes in multiplicatively here, we enable us to introduce a log, and the error that comes in multiplicatively, at the end of the day, it will be additive on a log scale. I'm going to say that again. The errors that come in multiplicative now will be additive on a log scale. That is when, after introducing log. That is exactly what I want to do here. Now, when you look at what I call equation, when you look at the equation 12, it's when the error comes in multiplicatively. Okay, I can call that exponential raised to power error. And of course, when I take the log, that's going to be possible. Take a look at that. Okay, and at the end of the day, when I take the log, I'm automatically going to have equation 13. Okay, now let us now fit equation 13 now. What are we trying to do? We've already fitted additive error structure. We now want to fit a multiplicative error structure. We are still talking about von Bertalanffy model. Okay, now this is my code. What am I doing? Introducing log. Oh my God, take a look at that. We are logging both sides now. Log, because of what we've done. Take a look at that. Now we decided to get the initial values again. We will run the model again. After, logarithmic transformation, we got a result now. Get a new result. We're also going to repeat what we get, the asymptotic confidence interval. Okay, so at the end of the day, let's compare something. The additive and the multiplicative. Okay, this is what it's looking like. Okay, that's what it's looking like when I can try to compare that. But let's now look at the assumptions. Like let's go back again and investigate. Oh my God, things are looking so easy now. The residual plot in the left. From fitting both multiplicative errors. Of course, we are focusing on the male Atlantic crocodile. So the residual plot, suggests a slight less heteroscedastic and slightly less skew with multiplicative compared to the additive. If you compare this with the other one, okay, you're basically going to see that this really makes more sense. That's what we're trying to say, even though they are very close. Okay? Now, is there any question? Is there any question? Go ahead. Well, can I say that again? We're not following?
We're doing nonlinear regression. Is it super relevant that we need assumptions of normality and heterogeneity?
That's a very good question. Even with the nonlinear regression, we still need, you know why we still need? Because we can never estimate parameter in a statistical model without having error incorporated. So statistical models are probabilistic model. And what makes it probabilistic? Because there's a random component. Therefore, we expect the random component to behave well. What do I mean by behaving well? Behaving well is, following assumptions. So you are right. That's a good question. Very, very good one. Except that there's one assumption we're not interested in, linearity. Of course, because we're already using nonlinear. But we still care about other assumptions. Okay. Now, the next thing I want to talk about now. Let's assume that we want to compare the growths in two groups. In this particular data set, we have male and female. we may want to compare. What do we actually, and when we want to compare the growth in two groups, we may basically want to have some assumption like, don't forget, each group has 3 parameters. You know, if you want to use Bertalanffy. So we're basically going to consider a situation whereby they have one parameter in common, or they have 2 parameters in common, or they have all the 3 parameters in common. We're actually going to have some subsets of modules, just like what we have in the conventional linear regression module. And that was what I'm trying to say here. The analysis of the multiple non-linear modules begin by fitting and checking the assumption for the general module. Now, this is what is going to happen. We have so many modules that can be compared in terms of maybe they have the 2 groups have 1 parameter in common, 2 parameter in common, 3 parameter in common, or they have their separate parameter. We first need to start with the general module. The general module that we're going to say, oh, they have separate parameters. The K here is different from the K here. L infinity here is different from L infinity here. The T0 here is different from the T0 here. Okay, and the assumption that we're actually going to investigate, okay, will be based on the general module only. The moment the general module assumption holds, then the assumption for the sub-modules we assume to be hold. Does that make sense? So that is what I mean here. That's why if the assumptions are met with this module, then they should be met for other subset modules. And let me now show you the different kind of modules that we can have. Now, this is the general one. Now, when you take a look at this, okay, when you take a look at this now, we are writing the von Bertalanffy module in 2 different ways. Excuse me? So we're writing that in 2 different ways. You know, see here, group 1, group 2, group 1, group 2, group 1, group 2. I want you to notice something here. On each of the parameter, we specify group 1, group 2 means they have their separate parameters. The parameters for male fish, different from that of the female. Does that make sense? That is what this guy is talking about. Okay? And this is another way, you know, if you don't want to write it this way, you can write it this way. Or what you're going to say is that you're going to say group on this parameter, group on that parameter, group on that parameter. That's a general one. Does that make sense? That's a general one. Now, the next thing now is, you know, okay, so like I said, it's a general one. Now, then you now consider other submodules. What if they have 1 parameter in common? If they have 1 parameter in common, it could be this guy, it could be K, it could be T0. If it is L infinity, okay, you are not going to see group. You're only going to see group in the other one. Is it not interesting? Oh my God. Take a look at that. When for common K module, you're also going to see that. You know, that K is not going to have a group. Okay, let's take a look at T0, right? Let's take a look at T0. For T0 as well, you're not going to see group on that. So now that is when they have 1 common parameter. What if they have 2 common parameters? What are the possibilities? I got 3 parameters here. They got 2 common. It could be L infinity and K, L infinity and T0, K and T0. And of course, the L infinity and K, okay, L infinity, okay, and K, if you take a look at it, it is only, you are not going to have a group on them. You're only going to have a group on T0. So just take a look at the parent, because I can ask you in exam to write a particular von Bertalanffy model for situation where they have 1 parameter in common and where they have 2 parameters in common, okay, and so on, like that. Of course, when you take a look at this, the common module, so we have that where there's no group. Now we have different kinds of sub-modules. If you want to go by this, we basically need to to start by, you know, figuring out the initial values, okay? So, right, that's a code. Want to figure out initial values? We have those initial values. And these initial values will be repeated. You know why? Don't forget, we got 2 groups, right? 2 different groups. So when they are repeated, just this guy, the same. Making 6. I'm talking about male, female, okay? Now, I'm going to write, like I said, we're going to start with the general module. Don't forget. Okay, and when we start with the general module, before we can go to the other sub-modules, we basically need to conduct absorption on the general module. The moment absorptions are met, we're actually going to assume it will be met for other sub-modules. Now, take a look at the code. Now, what are these absorptions that we need here is just like absorption, of constant variance and normality. Okay, absorptions of constant variance and normality. Okay, and of course, this is going to tell you can fit a residual plot and histogram, the histogram of residual. Okay, to be able to see, take a look at what we have now. I think, more or less looking kind of good. Okay, when you take a look at what we have, and I said finding the absorptions, are made for the general module, then each of the subset can be fit to the data with a result from each module saved in an appropriately named object. Okay, now I provided codes here. My TA is going to walk you through all this. Now here I've put into consideration different kinds of situation where there are one parameter in common, two parameter in common, the general one. So take a look at all of that. I need to study that. Okay, so when I do that, okay, so we're basically going to need a starting values, okay, that we actually have. Okay, now this is another code that I'm actually going to use to fit the module. After getting the initial values, I'll strictly go to the comparison. Now, the idea of the nested F test will be used here. You know what we're going to do? We're going to start comparing hierarchically two different models. We're basically going to start with comparing general with this guy here. Now, when you take a look at this guy here, this is talking about, the parameter that have, when you take a look at what I have here, I have a fit 1 KT and fit general. Okay. Now, the fit general, okay, the fit 1 KT is going to this guy here. Don't forget, in analysis of it, or when you are trying to compare two models, right? The model 1 is going to be the first one. Model 2 is going to be the second one. Now, there's something I wanted to pay attention to here. And let us see, when you take a look at here, there's a sex here, there's no have here. You have here, you have here, right? Now, if you take a look at this, you are talking about one having different length infinity and one without, the common length infinity. Now, when you take a look at what I have here, what is this guy trying to tell you? There's no more difference between, because when you take a look at this, a p-value means you are actually going with the first one, right? If you take a look at what we have been doing before. So, here we actually compare the general with, with this guy here, and you can see what we have, which is trying to tell us the general and this one, there is no much difference between them. If there is no much difference between the general and this guy here, then we're actually going to go with this guy. You know why? Because this one has more parameters because of parsimonious. You get what I mean? You see, if there is no difference between simple and complicated, then I don't need to go with complicated. I'm actually going to go with simple. Okay? Now, after that, the next thing I'm going to do now, okay, I'm also going to compare this guy with this guy. Don't forget, the one we compared before. I want to, let me go back. KT, right? Now, LT, right? What happened again? You see, the p-value, which means the first one is okay, right? Now, when you now continue to go now to the LK, don't forget, LK, KT, and LT, okay? So take a look at that again. Now, and that was why I said, the result indicate that each one parameter in common modus fit data well. Why do I say each parameter in common fit data well? Because we fail to reject the non-hypothesis. Does that make sense? Okay, so as well as a more complex model. And I said thus because each one parameter is common model is simpler than the general model. The general model will be removed, okay, will be removed from the consideration as the best model. So thus, at this point, it is known that the separate values for all three parameters are not needed for the two groups. What is the meaning of general? The general is going to say, oh, I need a separate values of the parameter for the two groups. That idea is nullified now. Is it interesting? Okay, if you are struggling, let me know. Okay, let me know if you are struggling. Okay, so that is where we are now. Now the next is, we now consider, we've considered the one having one in common, right? We now want to go to having two. That's why you say fit two. Does that make sense? Now you are now comparing that. We are no longer, the general is no longer in the picture. The one in the picture is those ones that were simpler, that we actually accept in favor of the general. Now, don't forget, between this guy now and this guy now, where is this guy coming from? From the first series of tests that we have done. The defeated general. Yeah, you see that now? That's why we call them this hierarchical, right? Now, here, this guy is a model 1, model 2. What happened now? Okay? Now, what happened now? We're actually going to go with model 1. We are going with this guy. That's the meaning. Okay? Oh, my God. Take a look at this when we get here now. Okay? When we compare the fit 2K with that, okay, what happened? We reject, right? Now, when we reject, and look at the way we are doing it. We are coming in a way, here, this is better, right? This guy that is actually, let me see if, okay, now we compare this with that same guy, and this is what we have. And in the end, and I say finally, the model with K and T0 in common should be compared to the common model to clarify whether L infinity differ between groups. Okay, now, where is the fit 2L coming from? The fit 2L coming from the fit, don't forget, okay, the fit 2L is actually coming from here, right? Now, if you now compare with the other one now, okay, with the one in common now, we'll take a look at that, we have this guy. So what does it mean? The results show very strong evidence that the common modules does not fit the data. Don't forget, the common module is in module 1. Okay? It does not fit the data better than the module with a separate L infinity value. So thus, the module with common K and T0 parameter, but separate, it means what we are recommending now for the two groups, the male fish, the female fish. Okay, we are recommending that we can use the same value for K and T0 for the two groups, but different L of L infinity. I want you to take note of that. Different L infinity. And you know what? If you don't want to go, or if you don't want to do this, just use AIC. Seek for the AIC of all modules. AIC of all modules. Look at the one for the smallest. Which one is the smallest? If you don't want to go, if you don't want to use this hierarchical comparison, you can use AIC. Now, what is the smallest AIC here? Correspond to which one? Is it this one? No, last one is 33. We are talking about the smallest. This one, right? Fit 2L. Let's see. That was what it was. The fit 2L. You see? The fit 2L was the one that they choose at the end of the day. If you want to save your time doing the hierarchical, just go for the AIC. Easy, okay? And at the end of the day, you basically have that. And because you've chosen that, then you now run that model. Okay? You run the model. No, that's okay. We've chosen fit 2L, right? Then you now run. You know, even in linear regression, when you choose the best one, then you now run your regression on the best one. Yeah, go ahead.
So, looking at what this actually means in terms of the fish population.
Yeah.
So it means that between the male and female fish, they have the same growth rate, but they have different maximum growth, expected growth.
Exactly. They have not only the same growth rate, they but also have the same T0, but they have different average. I want you to call it average maximum growth.
Okay.
You are right. That's what we mean. That's what we mean. For the fish, and based on the data, oh, time is flying. Okay, let me see. Oh, page 44 or 45. This is the last page. The last page just for us to see the values and the asymptotic results. Is there any question? That's all about Bertalanffy. On Friday, you're going to see different form of regression model. We still have a lot. Like I said, you're going to see your final result today. That result, oh my God, I have a lot of confidence in this class now. Okay. Make sure you stay safe and have a lovely day. Bye for now, everyone. Yeah. Yeah.
We spent a lot of time trying to like normalize the variables by itself because they were like totally not normal.
Oh, normal? Like when do you conduct a Shapiro wiki test of normality?
Yeah, and pretty much none of the variables we were using were normal. None of the